The name of this video is Degenerate Cases. If you remember from the previous video, in the previous video we studied qualitatively the problem of a cylindrical, finite cylindrical dielectric material with a certain length capital L and with basis with area pi capital R square, where the radius capital R, so length capital L and radius capital R, in presence of a uniform polarization vector P within the dielectric material, which again is generated by a certain E naught, which is the polarizing field, the external field that generates P in the same direction. All right. So that case is the most general case, and we qualitatively managed to draw the field lines of that object, which I remind you outside the cylinder is basically effectively an electric dipole with dipole moment capital P times the volume of the object, and inside there is a reaction field, also called a polarization field EP or depolarizing field, equivalent names for the same concept, which goes from the positively charged surface, which is on the right hand side, to the negatively charged surface on the left hand side. Now, what are the degenerate case of that scenario? Well, the first one is the infinite cylinder. So how do we obtain an infinite cylinder from that object? Well, clearly we keep R to be finite, whereas at the same time we extend capital L in the limit to become plus infinite. So it becomes an infinitely long cylinder. Let me sketch it to remind ourselves what this will look like. The dash line here means that it extends to infinite. Similarly on the right hand side, as such. And if I take a cross section here, it will look something like this, and here something like that. Okay, so in this case again we assume a uniform polarization vector P directed along the central longitudinal axis of this cylinder, which in fact coincides with the z-axis of a cylindrical coordinate system O bar r bar phi z, which we sketched in the previous example. So in this case, what happens is that we are going in the limit of what we studied in the previous example. So in the previous example, we had on the right hand side a positive charge density, sigma polarization on the right, positive, larger than 0. Whereas on the left, we had just a negative density, sigma p left, smaller than 0. Now, these two quantities, in the specific case we are considering now, they are pushed to infinite. So what is the total charge, the total negative charge, Q polarization on the left, is sigma p left times pi capital R square, whereas the charge on the right is QP right, the positive one, is going to be sigma p right times p pi capital R square. So these two charges are clearly finite charges. Why is that? Sigma is finite, as we calculated in the previous example. I remind you that it's nothing but minus the sigma PL is minus the norm of P, whereas sigma P right is plus the norm of P. So if that is the case, how do we what do we do with this infinite cylinder? Well, so sigma is finite, the areas pi r square and pi r square are finite, So these total charges, QP left and QP right, are also finite, because everything is finite in there. So we have two charges, one negative and one positive, which are both finite, but now they are pushed. So this was the example from the previous, so this was the case in the previous example. Now these charges are pushed all the way to infinite distance. This is to plus infinite, the positive one to plus infinite, and the negative one to minus infinite. So we have finite charges, QP left and QP right, which respectively go to minus infinite plus infinite. So what is the polarization field within this object, in this case, when I have a finite charge at infinite distance? So finite charge at infinite distance will result in a zero field within this object, because it's a source of charge which is finite infinitely far. So we know from Coulomb's law, in this case, infinitely far, 1 over r squared, clearly the field will go eventually to 0. Which means the field within this object, the polarization field or depolarizing field EP, is identically equal to 0. Obviously, this is true not only within the object, but also outside the object, which means this is true for each point, observation point, capital P, that is everywhere in space, that is inside and outside the cylinder itself. So this is a trivial case, okay? Where I have finite charge at infinite distance, obviously I end up with a zero field, as expected. What about the other more interesting case? The other more interesting case is that of an infinite disk or slab. How do we obtain an infinite disk or slab? Is the opposite, is the dual limiting case, the degenerate case of the infinite cylinder. So in this specific case, we are going to go with R, capital R, to plus infinite. So these areas become infinitely large, and at the same time, we keep L finite. So in other words, we have two planes, okay, which enclose the electric materials. Two planes can be thought as disks with infinite area, that's why capital R goes to infinite, or just two rectangles with infinite sides, it's the same thing. And within there is the electric material, which fills a regional space with capital L. So let us sketch this case here, to fix the ideas a little bit. So now, instead of being infinite in this direction, in the longitudinal axis along Z, is infinite along R, if you want to use the same cylindrical coordinate system as we've done before. And so in this case, the dashed lines are vertical. This is the prototypical example of the electric material, one of the simplest one. So the material now is within this object. Here it was here. All right. So in this case, again, we are going infinite along the radial direction R, if you want to use the same coordinate system as we've done in the previous video. Since we're doing the degenerate case, it makes sense to do so. Okay, so we have the material within these two infinite planes, so this means that in this specific case, this distance here is capital L. Okay, so here L goes to infinite, and here this distance was capital R. Okay, so L is finite, capital R goes to infinite, so I have this infinite slab, is called slab of dielectric material, or disk if you want. It's the same, geometrically in the end, it's the same concept, it's the same entity, the same object. Now in this case, we know that this was our z-axis. The polarization field P is uniform directly along the z-axis. So this is our P, which again is uniform that is, in this specific case, P vector can be written with respect to the cylindrical coordinate system as the norm of P vector in the direction uz. Okay, so we expect from the microscopic model, so we know that these are molecules, so we expect the molecules to stretch and be aligned with this P, with the negative molecules accumulating here on the left, and the positive part of the molecule accumulating here on the right. Therefore, there will be a reaction field, EP, the polarization or depolarizing field. So it's either you call it polarization field, or you call it the depolarizing field, or reaction field, we call it P. Generally, it goes from plus to minus, so it's opposed to the direction of P. So it goes as minus uz if you want, which makes sense because we know there is a shielding. The dielectric material tends to shield partially the external field, which eventually generates capital P, and we will come back to that E naught that generates P later on at the end of all these videos. All right. So now that we know that there is such, there must be such a field, intuitively we know that there are these charges here from the intuition of the microscopic model. How do we compute again? The charge distribution is exactly the same as we've done in the previous example. So again, we're going to have a sigma P on the right hand side, which is positive and is just the norm of capital P vector in absolute value. Similarly, there will be a negative sigma P left, which is equal to minus the norm of capital P vector, where we use the definition of sigma P is equal to P dot n. We've done this in the previous video, so I'm not going to redo that. Okay, one is negative and the other one is positive as expected from the intuition. Now, if this is the case, how do we solve this problem? We have a vacuum outside, a dielectric material inside, with these two charges. What about ρ? Rho P, as always, is 0 because we have a uniform P. We have seen already this in the previous video. So effectively, I can forget about that there is a dielectric material in between. I just consider two sheets of infinitely large sheets, two parallel planes of charge, one positively charged and the other one negatively charged. We have solved the problem of two parallel infinite planes of charge with opposite charges and also with same charges, as a matter of fact, but in this case opposite charge, of course, in FIS 242. Is the problem of the double layer charge, which also led in 242 to the Helmholtz double layer, which was the model of the surface of conductors, for example. All right, in some limiting case. So you can go back to 242 and see what is the solution of this problem, which is rather simple because you can do it by means of the superposition principle. So we know that in this case, in the double layer case, outside in the vacuum regions, there is zero field, whereas there is a field which is, each plane is sigma over 2 epsilon naught, multiplied times 2 is sigma over epsilon naught. And it has to be directed in this direction from plus to minus. So clearly, the electric field in this specific case, everywhere in space, is given by three contributions, factor 0 of course, for each values of z in the region on the left here from minus infinite to 0. And I suppose that the origin, we fixed the origin, well okay, we fixed the origin, in this case I fixed it to minus capital L over 2, and this one is plus capital L over 2, so we need to be careful about that. So it's going to be from 0 to minus capital L over 2, excluded. Now there is a discontinuity, so I need to exclude this point here, as we have seen in 242. In between, I have a field which is minus, this is EP, the polarization field, or depolarizing field, which again is minus sigma PL divided by epsilon naught. So if we express it already in this way, is minus the norm of P vector divided by epsilon naught, but this goes along the UZ axis, and so PUZ is nothing but P in this coordinate system, therefore we can, for simplicity, divide it as minus P vector divided by epsilon naught, regardless of any coordinate system if you want, and this is in the region between minus L half n plus L half, excluded, and is 0 for each point z in the region from plus L half to plus infinite, everything excluded because this is a discontinuity of the first kind, so we need to exclude it. Alright, so this is the result for the electric field, the polarization electric field within this dielectric material, and of course is 0 outside, as we know. Now, what I urge you to do in Piazza, I would like that you discuss the following problem in Piazza. Compare this to an infinite conducting slab made of a perfect conductor. So what happens in the case? Well, I already mentioned this in the previous video. What kind of shielding will the conductor do with respect to the field E? What kind of field am I going to have? Instead of EP, we call the ER. What is the magnitude of that field in the case of a perfect conductor? I remind you that perfect conductors shield completely, expel completely any external field. So with this, you should be able to remember also MEE from 242, readily solve this problem here and compare it to this one. I think this is the best comparison to understand with this simple example the difference between perfect conductors and dielectric materials in presence of a uniform polarization or a uniform external field, not if you want, they are related. So to summarize this video, the Degenerate cases, we started from the case of a finite cylinder with finite basis, with finite length, radius capital R, length capital L. We push it to the case where the length goes to infinite, therefore we have two charges, one negative, one positive, at infinite distance from each other, which means the field is 0 everywhere in this case here. Finite charge at infinite distance. In this other case, we have instead capital R goes to infinite, so we have effectively a slab of dielectric material with infinite length, with infinite size, a finite width, capital L. Since rho p is equal to 0 because p is uniform, effectively we end up having a positive and negative charge distributions on the two surfaces on the right and left side of this object. We can forget what is in between, similar to what we did in conductors. Typically for dielectrics you cannot do it because rho p doesn't have to be 0, only because p is uniform is 0. Intuition tells us plus minus, it makes sense with the calculations. So we have a reaction field which is called EP from plus to minus. What is the amount, the intensity of this EP? Well, it's 0 outside because this is effectively a double layer of charge, minus p over epsilon naught, minus, because it points opposite with respect to p, depolarizing, therefore, and 0 again on the other side. And I would like you to compare this with the case of a perfectly conducting slab, infinite slab of conductor, of course, in an external uniform field E naught, which goes in this direction as capital P. That's it.